Welcome to The Explainer. So, to melt or not to melt? I know, it sounds a bit like a philosophical riddle, right? But it is actually the ultimate engineering question when we're talking about piecing our modern world together. Think about the chassis of a car, a massive industrial pipeline, or the intricate framework of an aerospace vehicle. The way we join those metals completely dictates the strength, the durability, and really the entire nature of the final product. So today we're diving deep into the fascinating science of metal joining. Let's frame this whole explainer as a heavy-hitting showdown between two distinct, incredibly powerful philosophies of joining metal. On one side, you've got intense, localized melting, and on the exact opposite side, you have immense mechanical force without a single drop of liquid metal. So how do engineers actually choose? What are the trade-offs? And maybe more interestingly, what happens when these two totally different worlds unexpectedly collide? Here's our roadmap for today. First, the art of metal joining. 2. Fusion welding, the meltdown. 3. Pressure welding, solid state. 4. The ultimate showdown. 5. The resistance welding paradox. And finally, number 6, making the right choice. Okay, section 1. The art of metal joining, defining the baseline. Before we split off into our two different categories, it's absolutely crucial that we understand exactly what welding actually is. By definition, welding is the process of joining together two pieces of metal so that true bonding takes place right at their original boundary surfaces. We aren't just gluing things together here. We are talking about creating a permanent union where two entirely separate pieces coalesce to become one continuous structure. And this is a hugely practical, essential process for building, well, everything. From your weekend DIY hobby projects all the way up to massive towering industrial structures. Whether you apply heat, pressure, or a mix of both, and whether you add filler metal or not, the end goal is always the same. You're forming a permanent metallic bond that cannot be easily separated.
Moving right along to section 2, fusion welding, the meltdown, heating things up.
So, let's look at this first path. Notice how the base metal is actually being heated into a completely molten state. In processes like arc welding, an electric arc is generated right between an electrode and the workpiece. And we aren't just talking about a little bit of heat. This arc can hit a staggering 5,500 degrees Celsius. At that temp, the material at the joint is fully melted, it fuses together, and then it's allowed to cool and solidify. The key takeaway here? External pressure doesn't play an active role in this process at all.
In fact, it's super important to remember that almost all standard fusion welding processes demand three very specific elements. First, you need that intense heat source to melt the faying surfaces. Second, you absolutely need shielding, like a gas or a flux, just to protect the molten metal from the atmosphere. Otherwise, it oxidizes and gets all porous, which ruins the weld. And third, you generally need a filler material to ensure the joint is fully closed, especially if there's any kind of gap. Now, actually, scratch that. If no filler is used, it's technically called an autogenous weld. But as a baseline rule, those three pillars stand pretty firm.
Section 3. Pressure welding, solid state, forcing the bond.
Now let's completely pivot. Check out this quote, because it reveals something absolutely fascinating about this second path. In pressure welding, the metal never actually reaches its melting point. I know, right? Instead, the metal heats up just enough to reach a plastic, kind of viscous state. And then, external pressure is applied. It's this externally applied force that does the heavy lifting to create the bond. There are no glowing puddles of liquid metal and no filler rods are needed. It's just pure, immense mechanical pressure, combined with localized, non-melting heat.
A perfect example of this is friction stir welding. It relies entirely on incredible mechanical force. A rapidly rotating tool is pushed directly into the materials. The friction from that spinning tool heats up and plasticizes the metal. And as the tool moves along the joint, it literally stirs the solid-state metals together. It's an incredibly neat, environmentally friendly process. No toxic fumes, no blinding arc glare, no spatter flying everywhere, just seamless atomic diffusion right across the interface.
All right, section 4, the ultimate showdown, fusion versus pressure. Let's really look at the tail of the tape here and distinguish these two philosophies. Base metal state. Fusion means totally melted. Pressure means a plastic solid state. External pressure, completely irrelevant for fusion, but absolutely essential for pressure welding. And filler material. Standard operating procedure in fusion, but rarely ever used in pressure welding. Ultimately, it comes down to using the intense heat of an arc or gas flame versus leveraging the brute mechanical force of a forge or a friction tool.
So why does all of this actually matter out in the field? Well, because neither one is universally better. It's all about the application. Fusion welding is incredibly versatile, right? It easily fills large gaps with filler metal and can handle a huge variety of awkward shapes. But that intense melting heat inherently damages the surrounding metal structure, creating a weak point that engineers call the heat-affected zone. Pressure welding, on the other hand, keeps temperatures lower. Because the metal doesn't melt, it retains all its original strong properties. Plus, it's the absolute superstar when you need to join dissimilar metals. If you need a tricky biometallic bond between, say, steel and aluminum, which fusion welding heavily struggles with, pressure welding is going to be your best bet.
Section 5. The resistance welding paradox, blurring the lines. Just when you thought we had these two categories neatly boxed up, let's introduce a twist. Look at resistance spot welding. We have two opposing electrodes physically squeezing sheet metal parts together. That's massive physical pressure, which screams pressure welding, right? But hold on. A massive electrical current is passed through, and the natural resistance at the fang surfaces generates heat. And this heat is actually intense enough to cause the surfaces to fully melt inside, creating a fused weld nugget.
And that right there is the twist. Because those internal fang surfaces actually melt to form that nugget, resistance welding is officially classified as a fusion welding process. Yet, as we literally just established, it absolutely relies on heavy mechanical pressure to squeeze those parts together to achieve coalescence. It perfectly, stubbornly blurs the lines between our two categories. And just to put into perspective how important this paradox is, a typical car body has approximately 10,000 of these individual spot welds. This very paradox is quite literally holding the entire modern automotive industry together.
Section 6. Making the right choice. The future of joining.
So how do we actually apply this theory to build the future? Engineers have to systematically walk through these diagnostic steps. Step 1. Analyze the materials. Are you joining steel to aluminum? If so, you're likely heading straight for pressure welding, like friction stir. Step 2. Determine the structural needs. Can your design tolerate a weaker heat-affected zone, or do you absolutely need peak original material strength? And Step 3. Select the method. If you have large, uneven gaps to fill, fusion is your friend. But if you need clean, solid-state properties, pressure is the clear winner.
I want to leave you with this somewhat provocative thought. As modern manufacturing demands increasingly higher production rates and tighter precision, fully automated welding processes are completely taking over. Very soon, there will be more automated machines than humans in fabrication units. It's no longer just an experienced welder making a gut choice on the shop floor. It's computers running incredibly complex mathematical models and algorithms to predict the perfect weld parameters for maximum mechanical strength. So as we inevitably hand the reins over to the machines, will tomorrow's algorithms choose the fierce heat of a melting arc or the immense solid-state force of pressure to build our future? Thanks for joining me on this explainer, and definitely keep questioning how our world is put together.